this, can you all hear me? Okay, I assume so. Okay, well, I'm glad people managed to show up because I was a little stressed about that because this was set on a Friday and everybody I talked to actually said they weren't going to be able to make it, but I'm glad you folks could. I'm Brian Hook. I'm going to be talking about the Quake 3 Arena rendering architecture, mostly about the back-end stuff, not the higher-level data structures as much as how we generate the actual triangles from that information, how we optimize for OpenGL. So like I said, I'm a programmer with id Software. My prior background is I worked for Silicon Graphics for about a year working on their OpenGL for the PC. And before that, I was one of the first employees at 3dFX Interactive, where I architected their very early incarnations of the Glide rendering library. And as I mentioned earlier, I'm going to talk a lot about the architecture of Quake 3's rendering pipeline. So first, let's get the political crap out of the way. About a year ago, or even 2 years ago, there was a lot of worry that OpenGL wasn't going to be viable. Hardware vendors wanted to commit to OpenGL, but then, they'd sort of come up to us and say, okay, look, we're going to do OpenGL, but, you can't tell them that we're going to do it. And so we don't get in trouble, so we're going to try and keep this under wraps for a while. But OpenGL has managed to obtain enough critical mass where it is just pretty much here to stay. It is not a top-level priority, obviously, at Microsoft, but it looks like they're not going to be screwing with it because it would just piss off too many people if they did so. So thankfully, we have obtained enough critical mass that this is a viable API for developers to be using today. Quake 3 Arena is going to be using OpenGL exclusively. There will not be a software renderer. So, I guess we're really going to find out how well that's going to work out in a few months. For portability, we're using OpenGL 1.1, even though the 1.2 spec was released. I'm not even sure if there is a 1.2 spec implementation out there. The system-specific stuff, which is Windows system stuff, because OpenGL separates the windowing system initialization excuse me, and buffer swapping from the actual rendering of triangles. All that stuff is in separate subdirectories. We sort of just abstract all that stuff out. We're going to be supporting Win9X. We're going to be supporting WinNT. Both. Okay, time out just for 1 second. Uh-oh. Okay. Wrong slides. Hold on. Wow. All right, this is pretty much what we call the worst case scenario, where you go, all right, as long as everything's like good to go, we're happy, but unfortunately. Okay, sweet. All right, we're back. Okay, so we'll just pretend that didn't happen. Okay. Do you know how hard it is to act cool while you screw up that bad? It's pretty tough. I'm like, okay, oh, this is really bad. All right, so OpenGL is here to stay, yay. So people say, well, last time you bitched about DirectX, it was because, it was DX3, you're not giving it a fair comparison, blah, blah, blah. So I will acknowledge that DirectX has improved. DX7, DX6 have improved significantly. So if that's the case, why don't we use it? First off, they still don't offer any features over OpenGL that we really find all that compelling. On top of that, since we develop exclusively on Windows NT and they don't support Windows NT, there's sort of a mismatch there. And finally, it's just not as easy to use as OpenGL. They have made huge strides, but it's not even as close to being as easy to use. When we want to turn around and just whip out something and test out some algorithm or something, OpenGL is just sort of transparent. It's a great enabler. With DX, you sort of have to figure out how you want to render the triangles, what all the specifics are, and then when you're done, say, okay, does this look wrong because the algorithm itself is wrong, or does it look wrong because I screwed up something with DirectX? Okay, and we did that, so we'll pretend. Yeah, cool. All right. So under Windows NT, Quake 2 supported both DEC Alpha and x86. We anticipate supporting DEC Alpha once again on WinNT, assuming that there is actually hardware accelerator manufacturers supporting the alpha and with drivers that are capable of running Quake 3 Arena. We'd really like it if vendors such as believe Intergraph and 3D Labs would make sure that Quake 3 Arena runs on the AXP, but obviously that's going to sell like 14 copies. We're just doing it because it's easy. I mean, it's cool. I mean, yeah, so when we started Quake 3 Arena, I was actually going to switch to a Deck Alpha workstation as my primary development environment just to sort of make sure our code bases were cool, and we couldn't find an accelerator that actually worked. So I had to give up on that. We're actually going to support Mac OS. They are big into games again, as Steve Jobs has said, for those of you who saw the Macworld thing. Not only are they big into games, they're also big into OpenGL. That's going to be their 3D API. So for those reasons, we've decided to go ahead and support Mac, and we would actually like to do a simultaneous release with of the Macintosh stuff at the same time we do the Windows stuff. And we would also like to support Linux pretty much out of the box. There's sort of a problem there because their OpenGL situation isn't 100% resolved, but hopefully that will get fixed in the next couple months. So the first thing to establish is that Quake 3 Arena, once again, is an incremental improvement on graphics technology. It is not the huge leap that everybody saw from going from Wolfenstein 3D to Doom or from Doom to Quake. It is much more like the leap from Quake to Quake 2, but a little bit bigger than that, but still fundamentally a lot of the same architecture as Quake. It's still polygonal brush based with pre-computed visibility information, so that architecturally has not changed. One thing we've done is that our polygons are no longer split during the BSP process because we would rather trade off overdraw and get a bit more overdraw because we're not doing the cuts instead of generating all the extra triangles, because the amount of triangles generated during the BSP is, fairly significant. Being able to get rid of that is nice. Obviously, the big thing that we've added are the curved surface primitives, which I'll get into later. Because people have started coming out with more texture RAM, we've had to leverage this. We would like to leverage this with greater texture density. Traditionally, id Software games have been 8 texels per foot resolution all the way back to and including Wolfenstein 3D. We have opted to go ahead and give the texture guys the ability now to scale up to 16 texels per foot, and that should give us a lot more detailed textures. Our max texture size now is 512 squared, whereas before we told them to do 256 texels squared. One thing is that we opted at the very beginning of the project not to get stupid with our graphics tech. There were many directions that we could have explored that, basically would have gotten us a game, once again, doing about 15 to 20 frames per second, as is traditional for first-generation id game coming out. We could have gotten a lot more vibrant graphics. We could have done some pretty wacky stuff, but we chose not to go that direction because we knew that deathmatch was going to be important. As a result, we've pretty much scaled back our target for all this so that it can run fast. I mean, we haven't even released the game, and there are machines that can run consistently over 40 or 50 frames per second. By the time the game is actually released, it should be running extremely fast. We've added some new special effects. There's volumetric fog, portals and mirrors, which are sort of the same thing. Wall marks, scorch marks, things like that. Shadows, both sort of the cheesy, little blur underneath you shadow and also stencil volume shadows. Light flares, environment mapping. And we have a new general architecture called the shader architecture, which lets us use a text file to sort of describe how multiple passes for a surface are going to be rendered. Lets us specify the texture maps, the blend functions, texture coordinate sources, things of that nature. We can actually code up a lot of special effects purely within this text file without actually having to go and encode anything special in the graphics engine. That really frees up, it gives us a lot of creativity without having to come and, go to the programmers and say, hey, can you do this effect? And someone takes a few hours, gets it done and go, oh, this kind of sucks, and, let's not do this. Instead, they can sort of go and edit these shader files, apply it to a surface, and immediately figure out, oh, wow, okay, this looks good or this looks bad, all without having to impact the code. Another big thing is that we do have better lighting, although this is more of a subtle thing. We have specular lighting now. In addition, we have dynamic character lighting, which is something that we traditionally have not had other than, with Quake and Quake 2, a dynamic light would fly by, illuminate the light map, and it would illuminate the character. Now, depending on where the light is and its intensity and distance, it illuminates the character sort of correctly. The character model system is much like it was with Quake and Quake 2, which is the vertex interpolated frame animation, so it's not like a bone structure or anything like that. The difference is now that we connect the pieces together, so we have a head, a body, and the legs. And having tags that allow them to connect with each other, we can rotate them about these tags, so now you can actually tell when someone's looking down, instead of sort of them just pivoting like completely, now they actually bend over, look around. When they start looking around and they're looking down hallways, instead of just spinning completely, they'll turn their heads like that. So it's not really as much of a rendering thing as it was actually a gameplay thing. I mean, it's a subtle effect. People tend to like it. But it's nice, being able to look at someone and be able to see when he's sort of like scanning the area as opposed to just standing there or about to run or whatever. It really enhances the realism. We didn't use progressive meshes or any other type of technology that, that's very trendy right now for LODs, mostly because of space constraints. Because we're using the vertex interpolated frames, we can't start off with a 7,000 polygon model and LOD down from there, because it'd be 7,000 polygons times 100 frames of animation for that model. The other thing is that we built this pretty much from ground up to be optimized for OpenGL. We were no longer constrained by a software rendering architecture, and so we didn't have to make any trade-offs with that. As a result, we managed to go in and think things through clearly. Pretty much deleted the entire RefX86 that we had with Quake 2 and just pretty much started from scratch with this and just sort of re-architected everything from the ground up so that it would be extremely driver-friendly and hardware-friendly. One of the big things that we finally managed to accomplish that we've never managed to accomplish is that we have a unified back end. Previously with Quake and with Quake 2, you had characters and they would sort of go through their weird rendering path and their weird, rasterization path. Then we would have, the world was done a separate way, the sky was done a separate way, and they'd all sort of like filter out to OpenGL in their own different areas. Now what happens is we have a whole bunch of higher level primitives, such as world geometry, curved surfaces, models, the sky. We take all that, and each of those has its own routine to decompose that into basically a triangle soup. Then we just punch that, all of them sort of just ditch straight back into one unified back end. So the driver really never sees anything except this one path of triangles feeding into it. It's very easy for them to go ahead and optimize for that. They don't have to be all random going, oh, okay, they're doing something over here, they're doing something over there. It's a very simplified architecture, very clean. We have very minimal code paths, and which relates basically to this unified back end. Instead of having some new effect or some new rendering technology, we go, okay, now we're going to render things this way, and then it gets its own set of OpenGL state and GL calls. Everything sort of just, we're going to do, when we did curved surfaces, it's like, okay, this is a completely different representation than the world. Now we want to go ahead and feed this into our rendering backend. But instead of just taking the curves and rendering them ourselves, we sort of decompose them into the triangles and feed them through the back end. Another thing we've consciously done is minimize texture downloads. This is primarily for the obvious performance reasons. Hardware doesn't like texture downloads. AGP texturing has not been the panacea that a lot of us had really hoped for. And so, texture downloads aren't just a copy into the driver. A lot of them still just go ahead and put those on their local memory. And the other thing that hardware vendors will tell you that they hate are state changes. For various architectural reasons, state changes are exorbitantly expensive or can be. 3dfx has pretty lightweight state changes, but other people have extremely heavyweight state changes. So in general, if the application can avoid state changes, do so at all costs. All right, so to the specific details. The first I'm going to cover is the volumetric fog. Everybody has asked us for, give us fog, the standard hazy distance type thing that you see on flight sims and things like that. But we have never really felt that that is that compelling. It always seems to be fixed off in a distance. You really don't have control over it. It's sort of a hack. So we never really liked it. We wanted something where you could place basically a fog volume. The level designer can say, this area is a pool of fog, or we have some smoke near the ceiling, and that would hopefully look a lot more natural. Our fog volumes can be constant density, or they can be gradient, depending on their needs. Okay, so that last little bullet thing's sort of a mouthful, so I'm going to see if I can get us over to the fog area. you folks actually see that okay? Ooh, that's bright. Okay, so that is our volumetric fog. So it's a pool of fog as opposed to something that just goes off in the distance. So if we were using standard OpenGL fog, that little cross light up there would actually be fogged the same as that health ball down in there. All right, so the way we do this is that we do a third pass, assuming that that's all two-pass rendering where you're doing the light map, then your base texture. We do a third pass that's just an alpha blended triangle on top of it. There's nothing really tricky about that. We just go ahead and compute the appropriate density based on the distance from the viewer through the fog volume to that vertex. And just so you can sort of see that triangles within a fog volume, because we're doing vertex fog, actually get fairly heavily tessellated down there. You can sort of see the crease there where the fog volume sort of stops. And, I mean, obviously, if that was one big polygon, you'd get really bad linear artifacts. Triangles outside the fog volume, so that basically covers looking into a fog volume, and that's a relatively simple case. You just, slap another triangle on top of it. Triangles outside the fog volume are sort of done the same way, but instead of going through and doing an extra pass on all the polygons that you can see outside of the fog volume, which would require tessellating basically the whole world, all we do is there's actually a plane that defines the top of that fog volume that we tessellate that you can't see from this side because it's back-sided. But what we do is when you're underneath it, you can see it, and we compute the density to that plane, to each vertex on that plane. I'm just going to see if we can actually... it's kind of tough to see with all the other stuff going on. But, okay, you can sort of see it right there. It looks like there's actually a T-junction being fixed right there. So that is only visible from the bottom side. And what we do there is we basically go from the viewer. We compute the density from the viewer, or the distance from the viewer to the outside of the fog volume, and just use that as the alpha at the vertex for each of the triangles on the backside of the fog plane. So it's more of a screen space type thing instead of like having to go through and do it for every single vertex in the entire visible world. And as I said, this does require fairly significant tessellation of the polygons within the fog volume so it looks correct from the outside looking in. And from the inside looking out, you'd have to tessellate the top of the fog volume, the plane that's defined there. Okay, so this one's a little twitchy. Fogging blended triangles is not very, you can't just apply fog to it. But one thing that John realized is that if a material's impact is like the amount of contribution it adds to the frame buffer effectively, is proportional to the iterator values, then you can reduce the contribution for a fog effect. For example, if you're additive, you can compute your fog density to that and reduce the amount of RGB that's actually added in, and it just sort of magically works. And if you're a pure blend, you just reduce the alpha, and then less of it shows up, and more of what's behind it, the fogged, say, wall. If you have a window in front of a wall, the wall will start showing through more, but the wall is actually properly fogged, so this alpha part here, the window, it just sort of like dims down, and everything just works out. The math is just there, which is really nice. So the advantages of our technique means that we can get a true volumetric fog, which we, like I stated earlier, is something that we think is desirable over a distance-based fog. There are some disadvantages, however, because at the, actually, you can't see them up there. Well, if you look at those two lights, there's 3 little black dots there. And there's still 3 little black dots. And those are basically the result of a T-junction. Where the fog plane sits, we have to tessellate heavily beneath it, and what's on top is not going to be tessellated exactly, so we have the opportunity to get some T-junctions in there. So wherever there's fog, unfortunately, we get some little sparkles. That's theoretically fixable, but the cost incurred with that probably is not worth it. We also get the triangle interpolation artifacts. You can probably see it right there next to the staircase. They're a bit more objectionable when you actually move around. So you can still see this one sort of locked in there. It's not too bad, depending, obviously you can tessellate to an arbitrary amount. Sides of the stairs there, same kind of a thing. You can tessellate to an arbitrary amount in an attempt to get that, make that go away, but then you're just incurring a greater performance cost. But you can definitely see sort of the triangle artifacts, you know, over there on the sides. As I mentioned, excessive triangle count. Okay, portals and mirrors. Okay, so this is an example of a portal. So we can see what's going on in the quad room, but obviously you can walk behind here. And in this case, we can actually jump through it. Portals and mirrors are basically the same thing for us. The only difference between the two is what they're actually, you know, rendering, but they're handled identically. So yeah, it's location of the virtual viewpoint. In this case, the designers have gone through and placed like a virtual camera looking at the where the stairs were by the red armor and the volumetric fog, looking into the quad room. If this was just a mirror, what would happen is we just mirror the view position behind it, render the world as it would see. So that's the only real difference. The only trick there is, since we sample the PVS from where you are, in the case of a mirror, you have to make sure that the mirrored point, if it ends up outside the world, doesn't do bad things. So what we do is we attach to the mirror a PVS sample, so that when we're doing the mirror view, we just suck the PVS from the mirror as opposed to trying to suck it from, say, the wall. In this particular case, yeah, that would actually happen if that was in fact a mirror. You would see the whole world would end up being rendered, because if there's no PVS, we just draw everything. So they would have had to put a PVS sample point at the mirror so that when the mirroring was actually occurring, you would actually see the right thing. We only allow a single portal or mirror to be visible at once. It's not some technology thing. It's not like a difficult thing to solve, but you can and will get infinite recursion. And solving that's just sort of a hack, so we'd rather take a more elegant hack, which is only allowing one at a time. So the whole trick here is we render the whole world from the mirror portal's point of view using a user clip plane to clip off pieces behind the mirror. So if you have a mirror and you're mirroring the viewpoint behind the mirror, you don't want to actually see all the stuff that's behind the mirror. You want to sort of like see it from the mirror's point of view, but you don't want to see the back of the mirror or the armor sitting behind the mirror or anything like that. So we use an OpenGL user clip plane in order to achieve that. So then the frame buffer is basically filled with the scene as rendered from the mirror's point of view. Then we go through and just clear the depth buffer. Color buffer stays the same, so we still have the mirror's point of view. Then the next thing is we go back and we render from the user's point of view, the player's point of view, just the surface that describes the mirror's surface. We stencil in the depth buffer values at that point so that that will sort of stay there in space, or actually be, you know, depth buffered correctly. Then we just re-render the whole world. So what ends up happening is, if we were to be able to see this in multiple steps, you would see actually the whole part of, I mean, where the viewpoint is for this portal, it would actually render the whole scene there first, clear the depth buffer, then we go through and just stencil out that part, and then we go through and render the rest of the world, and it just magically works. It's really nice. So we stencil it without using the stencil buffer. We simply stencil it by drawing it first, clearing the Z buffer, and then putting in correct Z values for the new viewpoint. We've also added environment mapping. This is nothing magical. It's standard OpenGL style sphere mapping. We're currently computing this in the app, but the only reason we haven't been using a text gen as OpenGL provides is that we just haven't bothered implementing it. We'll probably go ahead and implement the text gen stuff before we ship, because that will take advantage of hardware transforms and lighting, and what we're doing right now does not. The other big thing are our wall marks. We've traditionally been known, I mean, oddly enough, we're sort of this paradoxical thing where everybody says we, you know, do really great graphics technology, but we also seem like adverse to putting in eye candy of any type. I mean, Unreal comes out and they've got, like, you know, flares and stuff like that, and we won't necessarily be for it, but people think that, you know, we're just kind of weird because we don't do it. And in the case of wall marks, which is basically shooting at a wall, this is the plasma gun, fades out. So when a big battle's been going on, it's like you get the scorch marks. We were basically guilt-tripped into doing this because of Half-Life. I mean, you have to understand, I mean, we are like so completely minimalist. I mean, actually, you probably understand that very well. But we're extreme minimalists when it comes to what we actually put into the game because we really like simplicity in design. So when Half-Life came out, all the level guys came in. They're like, hey, check this out. So are they better than you? And you're like, okay, fine. So we go ahead and do scorch marks. I mean, that's the thing. I mean, this is so, like, whack. Hold on, let's see. It's like, okay, gee, I wonder why we had to do this. So, it's like, yay, guilt-tripped into doing light flares, which actually are not working 100% correct right now. All right, so the scorch marks are basically, done how you would expect them to be done. We go through, we have an impact, we're going to draw a scorch mark, we clip the scorch mark to the actual face that it's on so you don't get scorch marks that, like hanging off the sides of walls or anything like that. We use GL polygon offset to deal with Z-fighting issues because obviously if we draw it right on top, I mean, it's just going to sit there and zipper and you're going to have horrible Z-fighting issues. So we use polygon offset to try and like just push it off just a little bit, enough so it gets drawn in front. Now the scorch marks are actually controlled by the client game. It's not controlled by the server. This is less of a rendering thing but more of an architectural thing. The reason for that is just because the sheer amount of network traffic to tell you, oh, there's a scorch mark that happens 6 rooms away from you would just be really, really exorbitant. So instead, the client game, which is the client-side aspect that communicates with the server, knows when like an impact occurs in the room and at what you're seeing. And it says, hey, cool, there's going to be a scorch mark there, and it sort of caches them and buffers them. The scorch marks do disappear over time. There is a fixed limit on how many there are. If you folks saw the demo running on the show floor, you'd notice that, in really intense scenes, you could actually see the scorch marks just start disappearing. That was just because they're expensive to have too many of them. And, some of the artifacts that you get as a result of that, since you don't know what's going on from the server, is that if there's like a huge battle going on in another room that you're not in, and you run over there and it's over, you won't see anything. There won't be scorch marks or anything like that. All you'll ever see is like scorch marks from where you killed someone or you were killed. And I mean, this applies to not only just scorch marks, but any type of wall mark that we want. Blood is going to be leaving trails and things like that. We also have volumetric shadows. This is the volumetric shadows are using the stencil buffer shadows that people have seen in SIGGRAPH papers and things like that. If people were here for the advanced OpenGL session that Mark Kilgard and Michael Gold of NVIDIA did, he talks about the way that the traditional stencil buffer shadow stuff works. He does a slightly different version than what we're doing. I'll get into that in a second. So obviously, if these are called stencil buffer shadows, they're going to require stencil buffer. We would ideally like 8 bits. I think we can use 4 bits, but some artifacts will be introduced as a result. This is a second-tier feature, which means that when we were writing Quake 3 Arena, at no point did we go, okay, these are super important. We're going to have to make these run fast, look good, not have problems, have to run everywhere. Curved surfaces are a first-tier feature. Have to run everywhere, have to be fast, have to look good. Stencil buffer shadows are something that John basically put in there in a day just to see if it would work. And since it requires a stencil buffer, it basically runs on Rage 128, TNT, TNT2. I think it should run on Promedia 3, but I haven't seen it running on a Promedia 3. And it definitely won't run on Voodoo 2 or Voodoo 3 since they're 16-bit. Won't run on an Intel i740, and actually won't run in 16-bit mode on pretty much any card, because if you even have stencil at all in a 16-bit mode, it's only a single bit. So let's see. This may be sort of difficult to see. So there, the quad damage is just casting a stencil buffer shadow straight down. The cool thing, it's actually self-shadowing, which may not be readily apparent there. So actually, the pieces of it are casting shadows onto itself, which is, immensely cool. It's a subtle thing, but it is immensely cool. So the basic technique works like this. I'll take that off so I don't get dizzy. You go from the light source and you determine the silhouette edges on the outside of the object. And this is basically how the one that Kilgard talked about works also. You take those edges, the silhouette edges, and you extrude those in the direction that your shadow would be going for a very long distance, and you make that into a quad. So basically, if you do this around the whole silhouette of the object, you should have like this, basically this extruded volume of the object of where it should be shadowing. You render all of the front-facing ones with your stencil buffer set to increment. You render all your back-facing ones afterwards with a stencil buffer set to decrement. Anywhere after that, and I know this is really difficult to visualize, especially with me just saying it and not, preparing enough to like give you sketches and stuff. But even if you do sketch it, it's sort of like not intuitively obvious either. But the net effect of this is that wherever there's supposed to be a shadow, the stencil buffer will be non-zero. I mean, assuming obviously that you cleared it out beforehand. And so at that point, your frame buffer or your stencil buffer should be set to zeros for anything not in shadow, ones or greater for anything that is in shadow. So then when you're all done with that, you just take a very large polygon over the whole scene, you blend it, we use a fairly light gray, and you set your stencil test to greater than 0. Then magically, everywhere that there should be shadow suddenly has a shadow because you've blended this big polygon over it. To try and speed things up, I mean, currently this particular build is a few weeks old, so it's incredibly inefficient. That's the reason why a lot of the IHVs weren't showing it in their booths with the shadows enabled, because right now, like right here, we're actually going through and computing the edge connectivity every single frame for that entire model, which is really bad. We should pre-compute that. On top of that, the models have multiple LODs, and we're just using, like, I think the highest LOD, and that's really bad too. For shadows, you don't need that level of resolution, so we should be using the lowest LOD all the time. Once we go through and optimize it, because it's a sufficiently cool thing that we probably should optimize it, but we won't depend on it for gameplay reasons, then it should be significantly faster. But it's still, I mean, even no matter how optimized we make it on our end, it's still going to be fairly slow, simply because the amount of overdraw and the extra transformations that are required. So the advantages of going with a stencil buffer shadow technique is that it's better than analytical approaches, since it's actually just based on what you render into the frame buffer. Analytical approach, something where it actually goes and does ray casts and tries to draw polygons that sort of go around the world, yes, would theoretically be better, but as our triangle densities just get huge, that's just not going to be a really, it's not going to be a very tenable solution to the whole problem. You're not going to be able to ray cast against millions of triangles every single frame. This also allows for self-shadowing, which, as I mentioned, is fairly cool. What this does show is this disparity between regular Gouraud shading and self-shadowing. The reason for this is that the shadows are basically based off of flat faces. Gouraud shading is based off the vertex normal. So you get this weird transitionary popping thing where the Gouraud shading, as an object rotates away from the light, the Gouraud shading will smoothly transition. But since we're just looking at silhouette edges for objects that are stencil shadowed, it'll suddenly be pop when the silhouette edge pops up, and suddenly that entire face is going to be in shadow where previously it would be in light. One of the problems is that shadows can cast through surfaces right now. I talked to John last night, and he said that he fixed that, so I guess it's a fixable problem. I'm not exactly sure what he did, but such is, my life. I'm not going to whine to you people about it. All right, so, well, I already did. So it is expensive since you have to determine the silhouette edges, like I said. I mean, if you're implementing this naively, like, we are currently, then it is expensive. But if you pre-compute all your connectivity, your adjacency information, it should be a lot faster. It is expensive since it requires a lot of overdraw, both because of the quads and the final screen blend. And as I mentioned, it does exhibit the artifacts that I mentioned between Gouraud shading, the inconsistency with Gouraud shading. Alrighty. This rotating thing like transfixes me every time I see it, and I like lose my train of thought completely. So we're just going to look at that. Well, no, that's bulging. Hold on. Let me just. Okay. All right. Okay. See, now that just looks like Doom, so I'm like happy. All right. So our rendering primitives. The big one, obviously, is our curved surfaces, which are quadratic Bezier patches. These are tessellated at load time, not dynamically, and this is for various performance reasons. We don't want to have to go through and compute the normals in real time and things like that. We will support, and it says that we do, but we currently do not, but we anticipate supporting row column dropping for dynamic load balancing. The reason we chose quadratic instead of cubic is that, quadratic, you're going to have 9 control points. Cubic, you're going to have the full 16. Is that it's just easier to manipulate. 9 control points is enough. And most of the level designers don't want to go through and actually have to, drag and stretch 16 points for every single pad. So it's a lot simpler. And the artifacts that you get, lack of C2 continuity and things like that, just aren't very noticeable in a game environment. The other thing is our MD3s, which is the Rev version of our MD2, which is basically our arbitrary triangle meshes. Our multi-part models are done with this. Unlike with Quake and Quake 2, we did not use Alias for this. We did use 3ds Max. We export to an ASE file, and then from the ASE file, we import it into Q3 Data. Q3 Data is our own custom tool, which then munges everything, does all the computations we need, puts it into MD3 format. We use a really, really simple popping LOD scheme. We have 3 LODs. It's based on the projected sphere size, so it's fairly naive, simple implementation. There's no noticeable artifacts with it. I mean, the big problem is that most people say you can see popping, but if you set it far enough away, you don't actually see the popping. And even though that theoretically gets rid of a lot of the benefit, in practice it still helps out a huge amount. I mean, in a really intense deathmatch, something like 2/3 of our triangles can actually be from entities, not from the world. And we do have the ability to do an LOD bias. So if you're on a slower machine that doesn't handle the throughput that makes it run at the speed you want, you can actually crank back the bias and have everything in its simplest form running around, and that can save you a few thousand triangles per scene. And on the flip side, if you have a real fast machine, you can crank the LOD bias the other way and have everything super detailed all the time. Now, obviously, there are character technologies that people have talked about that are just like way cooler, the morphing, skinning, bones, things like that. And so the question comes up is like, why didn't we do that? And basically, this was what we felt was appropriate for this generation for us. We chose to innovate in other areas. This was sort of the 80-20 solution, so we went ahead with this. Our next generation will probably be something a lot more fancy. We also have our new Sky, which is sort of a combination of the old Quake 1 Sky and the Quake 2 Sky. This was basically spurred by the need for having convincing clouds and an environment. So with Quake 1, the deal was that you had these clouds overhead that were kind of cool, kind of expensive, but still kind of cool. With Quake 2, went the other way, and we had the static sky, but with no moving clouds, but with very detailed mountains and things like that in the distance. So you kind of don't want to have to make a choice. So we just went ahead and did both. We're not using exactly like Quake 1 Skies, which had a really bizarre way of doing their projections. We have a slightly different way of doing our projections, which isn't quite as bizarre, where we project the cloud layer onto the skybox through a hemisphere. So it sort of gives you some level of curvature. So when it's flying overhead, you don't get that I'm a flat plane of clouds flying over your head feeling. It actually feels more like there's some volume to it. And the output, obviously, is heavily tessellated. Go ahead. It's actually not very easy to see on this level, I don't think. Okay. Okay. All right, this is a really bad example. This is two cloud layers, but with no skybox. I mean, they obviously don't have to do both. You can sort of see it. There's sort of like 2 parallaxing layers there, but I think it might be kind of difficult to see up there. But there's actually 2 separate parallaxing layers that kind of have this weird wavy feel to them, and that's actually an artifact of the affineness that we're doing there, because that's all the skybox looks like. We're just animating the texture coordinates right there. Wow, that's a lot of triangles. Sorry. Thankfully, you won't be playing from that point of view. So anyway, so you can see where we're just scrolling the texture coordinates all the way through this, but the geometry stays the same no matter what. So, yeah. Okay. All right, so for our static lighting, we're using light maps. Same as Quake 1, same as Quake 2. It covers the same world area as Quake 2. One light map texel covers 2 square feet. This corresponds to 132 by 32 texture block. Previously, it would have corresponded to 116 by 16 texture block, but since we doubled the texture density, it does cover a more number of texels, even though the world space units stayed the same. We are using direct lighting again, a la Quake 1. We're not using radiosity currently. It's for several reasons. The first is a stylistic thing. Okay, hold on. Sorry, I just don't mean to be so freaky about this, but I have these teleprompters right here, so every time I look over there, it's hey, cool, shotgun. Okay, cool. All right, sorry, a little idiosyncrasy there. All right, so we're using direct lighting. Quake 1 used direct lighting with a linear fall off. We're now currently using direct lighting with a more proper 1/r² fall off. But the stylistic thing with the radiosity is that with Quake 2, there was a complaint amongst our level designers, and I believe amongst a lot of our users, that world feels sort of washed out. And that's what happens. Radiosity basically brightens up the whole world because you're now bouncing light everywhere. It was extremely difficult for the level designers to get hard shadows. And that was one of the cool things about Quake 1 is, light would shine in through a window with a grate and you'd get these nice hard shadows, but everything just sort of mushed out and became very diffused. So there's a stylistic element to that. I personally prefer the direct lighting, even though I know it's far more inconvenient to work around when trying to do brightly lit levels. You can see things, but I also understand that you just can't do the drama with it. On top of that, it's just pretty difficult to do radiosity with the curved surfaces. I mean, there's just a host of technical issues with that, computing form factors and dealing with different subdivisions and all that kind of stuff. So it was also just a hard problem. So our diffuse light maps are basically done the way we've always done them, which is we take them, we do source times desc blending. We render them into the frame buffer, assuming we don't have multi-texture. We render into the frame buffer, and we render the diffuse one on top, and we just multiply the two. Our dynamic lights are handled through, we allocate 3 light maps that are just there for dynamic lights. They're D-Light 0, D-Light 1, D-Light 2. They're all 128 squared. Whenever we need to do dynamically modified light maps, we write into these and we upload them with text sub image. It is actually advantageous to upload text sub image, even if to use GL text sub image over GL text image, because text sub image uses the one that you've currently allocated. Text image sets your internal format, your dimensions, and things like that. Text sub image just changes the contents. If you were to actually use text image every single frame to upload these, the driver would actually have to go off and do a lot more, munging and shuffling around of things, and there would be a performance cost. So all else being equal, once you've created a texture, you should probably use text sub image if performance matters to you. We also have specular lighting in this. This is so amazingly subtle that most people just don't even see it. As an observation, specular lighting is really just a hack. I mean, it is a complete gross hack that is unfortunately presented in most textbooks as the logical way to do vertex lighting. All specular lighting is trying to do, when you get right down to it, is show you a reflection of a round light source somewhere. And that's just not very accurate when you have square light sources, things like that. So all specular lighting really is just a really bad implementation of environment mapping. Its only real advantage is that you can have dynamic lights moving around. And you can have the scene moving around and things like that without introducing obvious discontinuities between what you're seeing in an environment map and what's actually going on around you. Which, by the way, for our environment map stuff, we're just looking for the general chrome effect. We're not actually, we don't want you to necessarily be able to walk up to an environment object, look in it, and suddenly realize that someone's running up behind you, because we don't feel that's necessarily a first-order gameplay thing. So our specularity is encoded in the alpha channel of our texture. So higher alpha basically means that specific texel is really, really shiny and will reflect back a lot of light. If it's black, it means it's really dull and diffuse. Our color iterator, as we're rendering for our RGBA, stores the generated specular light value in the iterated alpha. So then what we do is we do that particular rendering equation. So if you look at the left half, it's basically the same thing that happens with regular everyday light maps, source times desc. So you're going to have the exact same thing as diffuse light maps. But on top of it, you're also going to have desc times source alpha. Destination at this time should just be your light map color. There won't be any texture in it. It'll just be your light map color. Source alpha will be your diffuse textures, your non-light map textures, alpha value, which is your specularity, times the incoming, because it's being modulated, times your incoming alpha value. And our specular lighting equation is just basically our the generic specular lighting equations you see in most textbooks. So what happens is that it will add a fraction of the light that was stored in the light map again on top in order to sort of saturate things. And it is view dependent. For our models, we do a very similar thing, but what we do is we do two-pass rendering, and we render the model gray shaded only, no texture on it at all. I mean, we use the white texture effectively. Then we use that sort of like a virtual light map for the model, and then go do the same thing that we did before. For our character lighting in general, if you recall from Quake and Quake 2, character lighting was just sort of like sample the light map and then modulate by a vector sort of like up and to the left. And there's like no really coherence between that and the rest of the world. So now we actually try and factor in dynamic lights if we can. So if there is a dynamic light nearby, we go ahead and use that to do the lighting. So what's really cool, and once again, it's a very subtle effect, is a guy standing there shooting the machine gun or the plasma gun. It illuminates the entire front half of his body, and the back half of his body gets very dark. And it's just very dramatic looking to see this very saturated white on the front. Okay, so if we don't have any dynamic lights around, then we will attempt to use the nearest static light, like those cross lights that you saw there. And if there's no static light, we'll use up and to the left in addition to sampling the light map. I mean, sampling the light map solves the problem 80% of the time, but when it doesn't solve the problem, it looks really, really bad. People would see this in Quake 2, where you'd take a bridge over water and you would turn blue. And because we're sampling the world, not necessarily the B model, or the moving B models. One other thing that we're doing now is that we're taking advantage of a technique called overbrightening. Our lighting programming assumes a dynamic range that's double what is effectively there. So you could think of it thinks of lighting in terms from 0 to 511 instead of 0 to 255. During rendering, on our side, we set the hardware gamma ramp so the back half of it, from basically 128 to the end, is saturated to 255s. The front half of it moves at twice the slope that you would expect. So instead of 0, 1, 2, 3, 4 that you would get with an identity gamma, it goes 0, 2, 4. The net effect is this, is that all the textures are doubled in brightness, but you only see the saturation if the texture is at 50% intensity or greater. However, our artwork in general is actually very low intensity. This has been sort of a traditional characteristic of our stuff, is that it is very low intensity. So in order to do this, you have to have the Win32 API of Get Set Device Gamma Ramp. This does work on Win9X, but drivers do not have to implement it. And drivers never implemented it because no one used it. We're using it, so hopefully drivers will implement it. We've gotten on the hardware vendor's case about this, and I believe it actually works pretty much everywhere. It's not difficult for them to implement. It takes like maybe an hour or two for them to do it. But since, anytime Microsoft comes in and says, with this Win32 API, it's completely optional, they're not going to bother. And so as a result, we've gone through and said, we don't require this overbrightening, but it really makes a big difference in just the dynamic feel of the entire world. So everybody hopefully is supporting it. Unfortunately, on NT4, drivers can't support it because when you call get or set device gamma ramp, it basically goes to a routine that zeroes out EAX and does a return. It doesn't even call into their driver. So it's very difficult, obviously, for a driver to support that, and we just have to learn to live with it, which is uncool because we develop on NT, so we don't get the cool saturated lighting effects till we go to our Win9X machines. The only weird thing is that since the Voodoo and the Voodoo 2 do not support the Win32 API since they're secondary display devices, we actually had to ask them for an extension, which took them 15 minutes to implement. And so we have a 3D effects extension to modify the gamma, which actually in general is a really nice thing because even if we don't do overbrightening, we can now control brightness. And on 3D effects, that's always been sort of a problem, that there's no real way of anybody controlling the brightness except to go in, I suppose you could do it with Direct 3D, but you could also go into the control panel. But if a user is upset because they can't see anything, then telling them to turn up their control panel brightness and then the rest of their games turn to white, they're not very happy. So we effectively gain dynamic range in exchange for losing some precision. And where this really shows up is if you walk into shadows, you see a bit more banding. But you get the really nice saturated lighting effects, which I'm sure, like that. So you go from here, from somewhere that's pretty dark, and then you can go out here and it's, fairly bright. And we never really had this ability to go between this very bright to very dark. We were either uniformly sort of bright, like with Quake 2, or we were uniformly sort of dark with Quake 1. We just didn't have the dynamic range. Let's see. Oh, bad. This is easier when you have two machines and someone else to shoot at to see this. I'm curious if you can even see that. Bad. Okay, do you see how that shadow flew by? So it's, a pretty cool effect. We really like that. So when you're in this big heated death match and like rockets are flying like this and you see people, running around, there's a guy running past you, you shoot, and you see this thing tear around them, and in this case, since it's partially environment map, you won't see it as much, but it also lights them correctly. So there's this guy running, or if you're standing like up here looking down, it looks just phenomenally cool. Where a guy's running, rockets are shooting past him. As a rocket flies by, he's being brightly illuminated on his right-hand side correctly. Then as the rocket flies by him, the shadow rotates and lengthens all the way around. And that just magically works because of the stencil buffer shadows and the way that we're doing our character lighting. And in addition, so when the rocket hits, you see, the super bright, saturated effect that's going on there. So right there, you can sort of see that being tossed up there. You just spend hours doing this. But like I said, it is fairly grossly expensive, and I don't think you can actually see the lighting that goes on with right there. Hold on a sec. That's kind of hard to see too. Okay. In a wall. Bad. Okay. So yeah, you can sort of see how when the explosion happens on the opposite side, this side gets dark and the other side gets the hell. Oh, jeez, sorry. My God, what the hell is going on? Speaking of which, so let me show you the specular lighting, which is amazingly subtle. So there, it's really bright, and if we, let's get somewhere a little easier. Okay, so there. Really bright, very shiny looking, and as you move away from that specific area, it gets brighter. No one ever notices this. But, that is the definition of complete second order effect. Unfortunately, it is somewhat at a first order price. Sometimes you notice it. I was really surprised when someone actually said, hey, I love the specular lighting on the tubey things. I was like, wow, you saw that? Okay. We also do cheesy shadows, which I think everybody here probably knows how to do. So you can barely see that. So you see that little dark splotch beneath you. And we make it, sort of fade away as you get far away and get darker as you go along. So this gives you still a feeling of depth. It's just basically glorified wall mark. The alpha is determined by the height of the object. We also gave the level designers this time around the ability to put in sunlight. If you recall from Quake 2, the whole world sort of turned into the color of the sky, which was just absolutely the wrong thing to do. So now you can have sky, which does contribute some color, but now you can also place a sun with a color and an intensity that just basically will mostly overpower, the entire sky. The sunlight effect is kind of nice in that, you get this kind of a thing where the sunlight just shines in, and it actually generally looks fairly realistic. And when you're playing the game, it's odd. When we first got the over-brightening in along with the sunlight, the effect was just a very complete effect. You would walk from the shadow into the sunlight, and you could almost feel it getting warmer. And I know that sounds really cheesy, but it felt right. Whereas in a lot of Quake and Quake 2, you'd walk from a dark area to a not as dark area, or from a lighter area to an area not quite as light. Here, you feel like you're walking from shadow into sunlight, and it's a pretty dramatic feeling. So this solved a lot of the yellow hell problem that we had with Quake 2, where the artist would get upset because they do this blue texture, and then you have a red sky, and everything just turned brown. It's just pretty grim. Okay, the shader architecture is sort of a big thing. That's where I talked about where we have a text file and we can assign material descriptions to things and say, okay, this is brick. So we're going to call it textures, Gothic, brick. And then we go through and we do an actual, a text file definition of these are the multiple maps, texture maps, how they're blended, how things are generated, things like that. So we actually shouldn't have called it the shader architecture. We probably should have called it the material stuff, but the way things sort of just like morphed and transmogrified over time, it originally started off as like a shading language, and it sort of evolved into a full material type thing. So now it's still called shader, even though it is actually materials. So we can do a lot of special effects with very little work. I mean, a lot of special effects that you see in the world, you don't see it as much in this level, unfortunately, are just the result of texture coordinate manipulation. I mean, that's it. You can, if you scroll, turb, scale, stretch, rotate your texture coordinates, and you do a lot of textures on top of that, it gives you a very dynamic feel. Our fire is not some procedural fire or anything like that. It's just like 4 flame textures that are being scrolled, turbulented, if that's a word, blended, and just sort of like mucked together at different speeds, different directions, and it looks very dynamic, very much like fire. And the nice thing about that is we don't have to upload a texture every single frame. We just do 4 passes, which in general is probably, for smaller surfaces, going to be far less expensive than uploading textures constantly. And like I said, the descriptions are in a text file. And, I wonder, well, I'm not going to tempt fate. I was going to say I could probably drop out and show you a text file. Or you can take the leaked IHV test and look for .shader files. I mean, I wouldn't, whatever. But, I mean, like, people haven't. And those .shader files sort of show what we do. But shader files tell you what kind of sounds are on that. So that's why, I mean, sounds obviously have nothing to do with shading. It's a material type thing. So you can say, okay, if anyone falls onto this, they're going to make metal footsteps. They're going to make brick footsteps, whatever. The editor image, so that you can specify a different thumbnail for the shader within the editor. It has vertex deformation information, because that's going to be constant over for all your stages that you're going to be rendering. It will be constant how you actually manipulate your vertices. Lighting information. If it's a light emitter, you want to say like what its intensity is and possibly what its color is. Well, no, not the color, because we get that from the texture. Miscellaneous other material global information. Tessellation density. If it's a fog brush, you can actually specify how much you want that to tessellate. So you can say fog test 64, so every 64 world units or something like that. And a sort bias for it, so that that has to do with our state sorting stuff. Basically, if 2 things resolve to being identical state and identical in all ways, so it's sort of ambiguous which one's going to be drawn in front of the other, but you actually have a preference that anything of this type material should be drawn in front of this type, you can actually push it a little further and give it a slightly higher priority in the sorting. So each stage, each individual stage when you're rendering can specify the texture map, which is just like a name of a TGA file, or $light map, which is sort of the magic name for whatever light map was generated for this, assuming there was one. Where the source of your texture coordinates are, so they can be generated through environment mapping, they can be generated from the actual texture coordinates for the surface or for your model, or they can be light map coordinates. So light maps are just a stage. So you end up saying your very first stage, map, $light map, text chord source, light map texture coordinates, or whatever we use as our syntax, and boom, you get a light map there. And then your next stage, you just go off and you say, hey, make it diffuse texture, map diffuse texture, texture chord source, texture coordinates for the world texture coordinates, and blend it with source times DAS. It just magically works. And as an aside, you do not have to go through and specify an explicit shader definition for every single surface in the world, since that would be horribly tedious. So we try and do things intelligently, and if all we find is a TGA, not an actual shader description, we sort of examine what's going on with the underlying surface and try to make our best guess as to what happens, and that saves everybody a lot of headache. Then you can also specify independently where your alpha and your color are coming from. They can be identity, so just make it white. They can come from a waveform. Currently we have sine waves, square waves, triangle waves. If they want it, we can add sawtooths, things like that. With a waveform, you can specify a base, an amplitude, a phase, and a frequency. They can come from the client game being the part of the game that executes on your side, responsible for visual presentation. So it may want to do some special effect. The renderer has no concept of special effects, so it'll do a special effect that requires it to send down its own computed colors, and then so look for it from the client game. Or you can have it generate the colors from diffuse and specular lighting. Or actually, you'd say RGB gen diffuse lighting, alpha gen specular lighting, since our specular is monochromatic. We theoretically can also do alpha and color modifiers. So once you generate your alpha and your text, or your alpha and your RGB, you can then say, I want to change it by some sine wave or something. So you can do lighting modulated by a sine wave or something like that. That's more implemented because it's orthogonal, but we don't actually use it because we can't think of any reason why we'd want to. So our texture coordinates can be modified in a ton of different ways. So you can specify it's going to be rotated, and so you can have like a spinning pentagram that sits on top of a piece of brick, and you just go off and say, rotate this at 1 degree per second or negative 1 degree per second, and it'll just sit there and start rotating. You can also enable or disable clamping of texture coordinates. You can tell it to scroll, and you give it units per second in both the S direction and the T direction. You can do turbulence, just like we did Quake and Quake 2 Water. You can tell it to scale, so that'll stretch it out. You can give an arbitrary transform, actually, of a 3x2 matrix. You can specify a blend function each stage. Whoa, that's a mess up. So that's not texture coordinate modifiers, that's stage stuff. But you can specify a blend function at each stage, which you actually just type in the OpenGL blend function names. Depth test, depth mask, alpha test, including, when not greater than 0, less than or equal 128, things like that. So we get this shader definition in, which is in this canonical multi-pass definition. We can then sort of examine the underlying hardware, look at its multi-texture capabilities and things like that, and say, okay, we can go through and collapse on this hardware for this. We're currently doing something that's very simple, which is just trying to collapse the first 2 stages if we see the easy case of a modulate or an add. However, John would like to go through and sort of like algebraically collapse everything, the whole thing as much as possible, which is kind of a lot of work, and I don't think it's actually going to gain much benefit, but hey, he wants to do it, and I'm not going to argue. So let's see. You can also specify for each of the shaders the polygon offset. So when we have a shader defined for a wall mark, all we do is instead of, when in the code saying this is a wall mark, we should make sure that we do polygon offset on it. All we do is we just go off and say, within the shader definition, this is what the plasma is going to look like. It's an additive saturate effect. It's going to do this. Oh yeah, polygon offset this. And then when we just draw the plasma stuff in the world, we just slap triangles there. During the rendering phase, it picks up, oh, this is polygon offset because that's what its material description states. It just magically works. All right. So we're heavily optimized for hardware acceleration. The hardware doesn't optimize for us, even though some people like to think so. We generally try and optimize for it. We're very knowledgeable about basically the limitations that hardware has, so we try not to do dumb things that will piss off the hardware. And as a result, we tend to get stuff that runs very fast. So we give up some things. It'd be great, yeah, if we could upload 4 megabytes of textures every single frame, but we can't, so we don't. It's not because our architecture sort of states that we don't need to. It's more like we make sure our architecture doesn't need to so that we can run fast. The other things we've done, as I said, state and texture changes are just really bad in general for hardware. That's just a good thing to work with. So we just try and avoid that. So we don't even do redundant state setting. We have like this meta function called GL state that we wrote that takes a 32-bit state vector. We examine it, diff it against the existing state, and if there is a difference, then we set it. So if we call, try and set the texture environment to GL modulate 10 times in a row, the API will actually only see that the first time. We also have the unified geometry backend, and because it's unified and the state stays the same for it all the time, we actually send down fully specified polygons at all times. This is more of a purist type thing, but basically, we're sending down RGB, we're sending back, RGBA to S&T, XYZ, pretty much for every single polygon, no matter what, fully, completely specified. Even if it doesn't need any lighting, say it's going to be effectively in replace mode, we don't put it in replace mode, we put it in modulate, and we set the colors to 111. And conversely, if we don't need it to be textured, we just go ahead and set it to a white 8x8 texture. And it just makes things really, really consistent and very fast. Our triangle meshes have a sort key that encodes the material state, sort type, things like that. So as we go through rendering the world, we take, here's a wall, here's whatever, a model. We dump all this stuff into these big triangle pools, and each triangle pool has associated with it a state. So we're left with, say, 1,000 triangle pools, each full of vertices and triangles, and each of them with a different type of state associated with it. Then we sort the pools basically on their sort, based off this sort key. So that way it automatically pushes transparent stuff further away. It pushes the things that have to be drawn at the very beginning, like portals and things like that, towards the front. And it just sort of magically works. It fixes a lot of issues. The state tends to be very consistent. Like I said, you can have a sort bias if you have some ambiguity between the two. As a result of all this work, we get currently 1.5 million multi-texture triangles per second on an ATI Rage 128 on a P3500 with about 50% of our time in the OpenGL driver. So that's not a contrived benchmark number. It's actually from within the game. Now, nothing else is really going on in the game, but it is still from within the game. It's not, some number that ATI handed to us saying, hey, here's a sphere and we're doing 1.5 million multi-texture triangles a second. We are actually doing within the game a full 1.5 million multi-textured and closer to about 2 million if we only do single texture triangles per second, which is a phenomenal amount of throughput. So then we have the back-end triangle renderer, which just takes all the triangles that we've collected, we've got them sorted now, and we pass them down. We pass them down in strip order, but they're not actually triangle strips. We sometimes have that information, sometimes we don't. We take all the information and we do a draw elements call. Now, we would prefer it if the driver actually looks for triangle strips. Even though it's a little bit more work on the part of the driver, overall it's still a win because it's to draw 1,000 vertices in the attached triangles. It is a single entry into the driver. So basically, we have a ton of time spent in OpenGL in one function call, and it's really, really easy for the driver people to optimize. It's a sort of a best case scenario for them. It's a nice, simple and consistent way of doing things. If we went ahead and did the strips ourselves, which we actually support if people don't have compiled vertex arrays, if we went ahead and did the strips ourselves, there would actually be a lot more entries into the API because we do a lot more begin, ends, and GL array elements and things like that, and overall performance would go down. Our vertex buffers are currently 1K vertices. They're 32 by the line for cache reasons. One sec. A byproduct of our triangle renderer architecture is that since we sort everything first, we are aware, we have information on all data that's going to be rendered before we've actually started rendering, which can come in very helpful. For example, we know through the bounding boxes that we look at during culling, what our Z range is going to be every single frame. So we can actually rescale our GL frustum so that we maximize our precision within the depth buffer every single frame. So now we don't get nearly as many Z finding issues that are far away, and we get pretty much full precision every single frame, which is really nice, especially on 16-bit cards. We have 3 back ends, basically, even though I said we only have 1. That was sort of like our technological ideal, but in practice we actually have 3. But everything sort of filters into one of them called TestN generic, except for the 2 most common cases, which are models and light-mapped walls. TestN generic is just like the most generic backend there is. You have vertex arrays, you have color arrays, you have texture coordinate arrays. It's always in GL modulate. If you don't need to light it, then you go ahead and you set the colors to identity. If you don't need texturing, you use a white image. As many of the arrays as possible are compiled if the compiled vertex array extension exists. And that's just sort of like the consistent but not optimal backend. For multi-textured light-mapped walls, and they have to be on a multi-texture system, it has to be a light map. There can only be 2 stages. I mean, it's very, very specific circumstances. Then we'll go through a slightly different path where we set the first texture unit to replace, second texture unit to modulate, and we'll disable the color arrays. It saves on some bandwidth. It earns us a few % here and there. One of the reasons we actually don't use GL replace all the time when we want identity colors is because of the variance rules in OpenGL. If you change your texture mode from one pass to another pass, there can actually be like LSB differences in Z during rasterization, and you will get horrible Z finding. So that's why we actually stay with modulate on both passes when we're doing multi-pass rendering. That goes away when you have multi-texture, so we go ahead and leverage that, use GL replace. And of course, there's the vertex lit case, which is our non-specularly lit models. That's the same as TestN generic. Looks the exact same to the driver, but we don't have to do a bunch of the cruft on our side that is part of the standard setup when we're going through our generic rendering path. So one thing we've emphasized with Quake 3 is that we would like to be more scalable. We're not as scalable as up as we would like to be, but a lot of it's just a data limitation. And once people are running this at high res, we can't make our models more complex unless we, do subdivision surfaces, at load time or something like that, which we're probably not going to do. So we can scale on fill rate. If you don't have much fill rate, or if you have a lot, you can obviously just change your screen res. In practice, we've noticed that actually doesn't make a huge difference. A lot of people cannot tell the difference between 640-480 and 1280 by 960. It's like a 10% increase in image quality at 4 times the cost. But if you are suffering from a lack of fill rate, then it might be in your best interest to run at 512-384 or even 400 by 300. But this is for like fairly old hardware, Voodoo 1, slower hardware, Promedia 2, Rage Pro, things like that. Although Promedia 2 actually might run very well if we're using our vertex lighting option. All that is, it makes the world render in a single pass. And we ditch light maps altogether. We still keep them in memory so that we can properly light map sample characters as they're running through the world. But now we just actually sample the light maps at vertices. So you get all these horrible vertex artifacts because it's basically a Garot-shaded world, but it is significantly faster, halves your transformations, it halves the fill rate requirements, and in the case of Promedia 2, it compensates for lack of a fundamental blending mode that we would need to do light maps, which is why Promedia 2 wasn't very well supported under Quake 2, except in the model light map case, which was just a hack for Promedia 2. This is still sort of a hack, but it's a hack for anything that doesn't have that blend mode or anything that's just pretty slow. For people who are running on a Rage Pro, which is not the gamer's card, but there's like 27 million of them out there, this is really going to make the game pretty much playable for them. If you are limited on throughput, you can obviously change your LOD bias on your models, so you can just push it further away. Instead of having the 1,000 model guy running around, you have the 300 polygon model of the guy running around. You can also control the subdivision density for the curves. So instead of having them tessellated right now, they're at sort of the default tessellation. You can crank down the subdivision, and then they get very, very angular. Reduces the amount of triangles in the world, especially obviously on heavily curved levels, fairly significant amount. And if you're CPU bound, you can turn off dynamic lighting. That is really costing us a lot. I think John told me that it's costing us about 25% now on the client side, which is a huge amount of time to be spent on dynamic lighting. So if you turn that off, we actually managed to get on a Rage 128 with P3500 running at 512-384 with our LODs cranked down, but otherwise, and with no dynamic lighting, but otherwise, basically like you see there, we actually managed to get one of our demos run at 60 hertz the entire time, I think. I think it popped down a couple times, but it was very close to 60 hertz the whole time. So by the time we ship, it may be possible for people on high-end systems to be running at 60 frames a second all the time, which would just be very, very cool, because then this would be the fastest game that it has released given the current state of the hardware at that time. Quake 1, was running 15 frames a second. Quake 2 was running not much faster, 15 to 20 frames per second. But basically the amount of innovation we've done and our need to be scalable back down has been outstripped by the ability of CPUs and of hardware accelerators in general to provide us the bandwidth to run this at even faster speeds. We do support multiple CPU architectures. One of the reasons to do the Mac OS stuff in parallel is it sort of keeps us honest when it comes to NDN issues, because it's really easy for that kind of stuff to slip. So from a purity standpoint, we do like being multi-platform all the time. So all of our computation-heavy code is pulled out into a single file called trcalc.c. And that's where fog density, perturbations, client-side transforms, lighting, things like that are all done in this file. So in theory, we have the C version. In theory, we can go off and do the Katmai or SSE now and the 3D Now stuff, and we can just optimize that one file. We select which CPU. We have the CPU detection code in there. It actually sets a CVAR. We can select which calc function we want to go to, and then we'll magically get optimized for that particular platform depending on when you run, because we just point it to a different proc table. However, as 50% of our time is being spent in the OpenGL driver right now, but that's on a phenomenally fast OpenGL driver on a very fast machine. On more normal machines, we're seeing about 70 to 75% of our time being spent in the OpenGL driver. So no matter what kind of optimization we do on our end, such as KNI or 3D Now optimizations, the biggest gain is from the drivers being optimized to support Katmai, the drivers being optimized to support 3D Now. We will see a far greater increase in performance through that. Okay, so about our OpenGL support. The mini driver must die. We are really, really aggravated by that thing. We do not plan on supporting the mini driver. We definitely do not plan on supporting the D3D wrapper, and would probably flip out if Microsoft released another one. We like the mini driver because it gave OpenGL an early boost. When GL Quake was released, mini driver was the only option we really had. Unfortunately, by sort of the other side of the coin, it really sort of anchored future development. Unfortunately, other developers went off and tried to develop OpenGL code on the mini driver, which is probably a really poor idea. Unfortunately, they really didn't have any other option at the time. So, it was a win in the end because OpenGL survived, but we are sort of suffering for it now. Quake 3 was written on Intergraph NT workstations. They were just recently upgraded for some of us to dual processor P2400s. However, the Intergraph Realism cards aren't that fast. 60 megapixels, that's about in the same league as an Intel 740 that is 30% slower than a Voodoo 2. So that sort of keeps us honest. We don't get too crazy with what we're doing because we have pretty poor fill rates on our primary development machines. We do not link to OpenGL32.lib and call GL calls directly. We go through basically a humongo amount of function pointers called QGL. We do this obviously doing the load library, and then we do wiggle get proc address and just regular get proc address for the pieces that we need. Now this was necessary for one major reason, and that was because of the Voodoo and the Voodoo 2. There's no way to use the ICD, the standard anointed Microsoft OpenGL mechanism, and get to a Voodoo 2 or a Voodoo because there was no enumeration capability. So if you have a system with a Riva 128 and a Voodoo 2 and you want to play on the Voodoo 2, you would have no way of doing that using the standard ICD mechanism. So that's the main reason why we're doing that. A nice side effect of that, though, is that we can intercept the QGL calls and route them into our logging stuff, so we can actually keep a pretty good log of all of our OpenGL calls and see when we're getting too crazy on one specific area. We use the full OpenGL transformation pipeline, so we will be able to leverage hardware transform and lighting in the future, and actually we leverage it today because our Intergraphs do have hardware transform and lighting. However, their transformation rate with these $1,500 DSP boards is still lower than a P3500 on a Riva TNT. So not sure how much of a win TNL is really going to be. We do not use the OpenGL lighting pipeline. We've been pretty vocal about this. We feel that OpenGL lighting model is basically one lighting model for a very specific area, CAD, flight sims, things like that. The Vertex model is not very appropriate for indoor rendering. We do not use the OpenGL fog capabilities for the reasons I outlined earlier too, whereas we don't feel that fog based purely on distance is the right way to go. We do use OpenGL Stencil. We use it for the shadows, like I showed you earlier. We also use it for overdraw measurement, which I talked about, not in a plan file, and which you can find pointers to it on the web. And it's basically you have it set up so that you clear the stencil buffer and you have it increment every time a pixel is drawn. And then you can go back, read back the entire stencil buffer, and be able to figure out your average depth complexity over the entire scene. For our texture management, as I've harped on for quite a bit, we do minimize our texture changes as much as possible. We do use GLTeX subimage instead of GLTeX image 2D in order to maintain the internal formats and make life easier for the drivers. We still don't use GL prioritized textures. Theoretically, we should. There's some things like the console, for example, can reside in system memory. It does not necessarily need to be on the card memory because it's not down all that much, and it does consume quite a lot of texture RAM. And unfortunately, it's the very first thing we upload, so if they're just doing like a real basic scheme where they're filling up their local memory, then overflowing into AGP, then it's going to be residing on the faster local memory instead of in the slower AGP, and no one really cares how fast you draw the console, especially if it's only going to be 15-20% slower. We do support various OpenGL extensions. However, it's important to note that we wrote this on a completely vanilla OpenGL. Intergraph is a workstation company, and as such, doesn't really care too much about supporting Quake 3, so they're not going to go off and do extensions to make our stuff run faster, because it's not going to sell any more Intergraph workstations to Hewlett-Packard. Or well, actually, HP obviously wouldn't buy it from Intergraph. So, well, from some other large company that would have a need for workstations. Extension support is completely optional. We don't require someone to go off and implement an extension. We don't require anyone to implement any form of extensions in order to run. We will always run on a vanilla OpenGL 1.1. We do support the ARB multi-texture extension that was introduced with 1.2. That's how we leverage multi-texture. There's various texture environment extensions to let us blend between the different texture units in different ways. It hasn't been fully resolved yet, but we anticipate that one will come around in a few weeks or a month or two, and we'll go ahead and support that for some of our twitchier or multi-texture type stuff. We also do support S3 TC texture compression. However, we don't support it as much as they'd like. We don't go off and make 2K by 2K textures and pre-compress them, then download it, and things like that. We basically just say, if you can download this to your S3 texture compression, hey, that's cool if you can do it dynamically. And if another compressed texture extension comes out, we would like to support that too. We also support EXT swap interval, which lets us control whether or not you VSync. It's just handy for benchmarking. Also gets you a little bit better performance if you're willing to accept the tearing. And like I mentioned earlier, we support 3dfx's gamma control stuff, which is an exact analog to the Win32 stuff. So we actually just have like 2 separate function pointers. Okay, so I'm going to go through some specific hardware comments. Note to any IHVs that are here, Intel has been working really hard on just not optimizing Quake 3, but like optimizing OpenGL. The contact there is a guy named Igor Sinyak, and he asked me to put up his email. So if you're a hardware vendor and would like Intel to assist you with driver optimizations for OpenGL, please contact him. He's a really, really smart guy, and he's made things go very, very fast. All right, so sort of the rogues gallery. 3dfx, Voodoo, Voodoo 2, Voodoo 3, Banshee. We will obviously have to support that. That's what the hardcore gamers have. They have a very good OpenGL driver. It lagged for a while, but right now it is very good. 16-bit, I've harped on that quite a bit. Wheel deal and things will not look quite as good on their stuff as it does on a Riva TNT running in 32-bit mode. You won't get stencil shadows on their stuff. S3 Savage 3D, we actually really liked the Savage 3D. Thought it was a pretty cool chip. I mean, it wasn't the best. It was a shame it didn't get more OEM wins, but it supported 24-bit rendering. It had the features that we needed, and it ran at a pretty good pace. Savage 4 actually looks like it's going to be really good. It has very fast multi-texture all the time, and what's really cool is going to be available on a laptop, so that's going to be cool. I hope I could say that. I just realized that maybe that's not common knowledge, so rumor has it that it'll be on a laptop. Yeah. So PowerVR PCX2, no, that's just too bad. Hey, I mean, Quake 2 barely ran on that thing, so there's no way that we're going to be able to get it happening here. PowerVR's next generation hardware, no idea, because they don't talk to us. 3D Labs Promedia 2, Promedia 3. Promedia 2 is going to be supported on the fallback path, and I mean, I am amazed that it runs on a Promedia 2. Yeah, it's in the cheesy Vertex-like fallback path, but it runs like reasonably quickly because it's half the fill rate that they need. We're running pretty much an optimal path for them because they were pretty slow at blending. But they should be able to run it like a full 40 or 45 megapixels, and that's pretty good. And transformations are reduced, things like that. So anybody with Promedia 2 should be able to play the game and have an enjoyable experience, although not necessarily like the rocking experience you're going to get on a Riva TNT 2. Speaking of which, for those of you curious, this is, I believe, running on a Riva TNT 2. And I would like to thank NVIDIA for loaning me this machine at the last second. Actually, this may just be a regular. This just may be a regular everyday TNT. And not necessarily a TNT 2, and this is a Pentium 3 machine. Oh, and this is running at 8x6. The Pentium 3 should be good, but we don't have a board, so we can't say one way or the other. Pentium 3, Promedia 3, the Rage 128, the TNT/TNT 2, Savage 4 are all looking to about have roughly the same features and performance, which is good for us, bad for them. And I care more about us. No surprise there. Okay, so Rage Pro, really bad actually image quality, really bad performance, but we still support it because it owns the market. I mean, every machine you buy today, just by default, comes with a Rage Pro. So we do support it. It actually runs our stuff in like the full mode. I mean, theoretically, it has some form of multi-texture too, in theory. But in actuality, what we're probably going to end up doing is running it in the Vertex lit path. I mean, people still can run it in the normal path, but the Vertex lit path is probably the best thing to do for that. Rage 128, feature complete, very fast OpenGL. Rage 128 does rock. V2200, they didn't sell very many of them, not terribly relevant. We would like to support it just because it does have a history with rendition. It was good hardware for its time, but right now it's currently extremely throughput bound. I mean, feature-wise, it actually was a bit superior in many ways to the Intel 740. It had about the same fill rate. It had 24-bit rendering, things like that. But the V2200 just, it doesn't have the throughput of the 740. The 740 has like the most insane driver in the world. I mean, it's like an $89 board, and it only does like 500,000 triangles a second peak, like the board. That's all it can do, and it's doing 500,000 triangles per second. So, I mean, the driver guys who did that are just like making that board scream. So, mentioned 740, very high quality OpenGL drivers. I mean, here's the creepy thing about the 740. They have not given us a new driver since last October, and Quake 3 still runs on it. And, I mean, we're doing all kinds of crazy, wacky stuff here, and, they just did it. So, it's not like, I mean, sometimes things break, and drivers will have to be revved because they, if code is never executed, there's no way it has been debugged. And the 740 is just rock solid. However, it is 16-bit only. It's fairly average image quality, not as much precision as we would like. But it does also have AGP texturing. As far as I know, it's like the only board that does pure AGP texturing. The Matrox G200 and the G400 have really good visual quality. Their hardware specs actually look reasonably good. The G200 is basically like a single texture Voodoo 2. They have, like I said, very nice image quality. They have been sort of a sore spot for us because they supported the D3D wrapper, and their ICD wasn't very good. But as of about a week or two ago, I mean, they've managed to get their ICD just screaming. So it looks like it's going to be a very good viable board, similar to a Banshee, possibly even better since it supports 24-bit rendering modes. And it should be a really good board. Riva 128, it's got a pretty solid OpenGL driver. Image quality just pretty much sucks. I mean, anybody who's had a Riva 128 knows exactly what I'm talking about. So I won't harp on that. And then there's the Riva TNT, TNT 2. It's feature complete once again, very fast OpenGL. Not as fast as ATI's currently, but hopefully, there'll be some competition there. But it is the second fastest easily. I mean, no one's even close to them right now other than ATI. And it's very robust. So as far as recommendations go, if I was an OpenGL developer who did not feel like dropping $15,000 on a workstation, I would probably just pick up, if I was starting a project today, a Katmai system, P3500, and I'd probably just put a TNT or a TNT2 in it. And I know a lot of people who've been developing OpenGL apps and OpenGL games on TNT, and they're amazingly happy with it. NVIDIA has been far more committed to OpenGL than any other IHV, and it really shows. And it's not committed to OpenGL to make it happy. There's a lot of OpenGL people at NVIDIA who just like OpenGL. People like Michael Gold, Mark Kilgard, and a bunch of other ex-SGI people, basically, who are over there that are very much pro-OpenGL. And so, I mean, I would pretty much go with a Riva TNT if I was developing from scratch today. The Rage 128 has exhibited some flakiness, but, I mean, it's got insane performance, but it still has exhibited some flakiness. And for lower-end machines in Intel 740, probably do a really good job. Okay, so I'm going to wrap this up. So what we are finding today, and this is going to probably seem really weird to you folks coming from an id Software guy, is that the technological advances that we're seeing are pretty much second-order effects. We're cranking, I think the average Quake 1 scene has something like 700 polygons or something like that. And like this scene right here is doing like 5,300 triangles in the whole scene. So, it's like over 7 times as many triangles being rendered here. And, those, a lot of that's just the curves right there and the grill near the top. And this is without us splitting polygons with the BSP, so that's even worse. Imagine what it'd be like otherwise. So we have 7 times the triangles per scene. We have way more textures and things like that. But to the average person, and not just the twitchy game developers, to the average person, there isn't a huge difference between what you're seeing right there and Gloomkeep on Quake 1. So when you went to Wolf to Doom, you could show it to your mom, and she would go, "Oh my God, this is like amazing." And it's like your mom, right? There was no arguing when people saw Doom. That was something completely and radically new. And Quake was sort of the same thing. It had the light maps, these dramatic shadows, and people were like, "Oh wow, this is just amazing." But ever since Quake 1, basically we've mastered. When you're missing an entire dimension, that's noticeable. That would be the first order effect. So going from 2D to 3D was a big step. Then from 3D to better 3D to better 3D, you're just not noticing it. So you have all these things that we spend a lot of time researching and implementing, but are giving us really, really incremental improvements. They're not really helping us. They're not really like the super insane thing. Okay, so it's like, here's our little bulgy, gooey, creepy thing. And, that's a curved surface. It's using our shader stuff. We're not doing that in code. Obviously we are, but the shader for that says deform vertices using this bulge with this phase, this amplitude, this frequency. And, it's really cool. Hey, and you know what? It's got specular lighting, which you can barely notice when you're moving around it. And like fog here, you, me, we'll go, hey, cool, volumetric fog. You can walk into the fog and look up, out of the fog. But you know what? To the people buying these games, for a lot of them, it's like, oh, fog, like in my, flight sim. And they don't know the difference because it's just fog. And to us, it's a big deal that fog goes up and down now. To them, it's like, whatever. It's fog. Not a big deal. So it's only really a big deal when you're the person writing it and you're really proud of it. It's like, hey, isn't this cool? It's like, oh, you didn't see that. That's our really not done lightning. Okay, hold on. Other things, does, that really, is that going to be, no one's going to look at flares and go, oh, wow, that was just like, Wolf to Doom. Granted, it's not as difficult, but, the things, you have arches. And part of this is that, people are used to seeing archways, and now that they're really curved, it's, oh, cool, an arch. The average user never actually said, oh, it's kind of weird that there's no curves on here. The developer said that, but the average user never said, oh, there's no curve here. And if there's shadows, hey, cool, shadows. But, it's really... is not one of those things that your average user really picks up on. And I realized this when people would send me email and saying, why does Forsaken run 3,000 times faster than Quake 2? And they look the same. That's not the bag on Forsaken. Forsaken's a good game, and it's a good looking game. It's a very impressive looking game. But to me, I just look at the technology and I go, well, we're doing light maps, blah, 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 blah. And people go, well, Forsaken looks just as good. And it's like, wow, people think that, and if that's the case, then maybe what we're doing that's so technologically advanced and so much better isn't really buying us that much. So, this has been a point of stress for me for a while, and that you have 7,000 triangles visible in a scene or 30,000 triangles visible in a scene, but the scenes are not getting 5-10 times better. So what this really means is that technological advances really need appropriate content. And in the old days, a few years ago, it was always the artist coming at you saying, look, man, I've got this cool 256 square texture. Why can't I use it? Or why can't I do this in RGB? Or why can't I do this way? And, it was always because machines aren't fast enough, because the hardware's not fast enough, because no one knows how to do it, or because, I'm not that good a programmer, or whatever. It was always the programmer's fault indirectly one way or the other. Now what's happening is the curve is almost beginning to cross over, where the programmers are coming up with like really wacky stuff like, the curved surfaces and things like that, things that are really cool to other programmers. And no one is noticing. And so when you start supporting really high-res textures, you need high-res art. You need people that understand, there's going to be a greater thing about dynamic range. If your average texture is only 25% intensity, you are not getting anything for dynamic range. You need level design that maximizes the given triangle budget. Unfortunately, I'm going to be indirectly ragging on Christian, so he's going to hate me. But an example of this is, and this is like an early version of a level, so it's not really a fair thing to say. But you're running around with no mouse pad. Okay. You're running around doing things, and you're killing stuff, and you're shooting at things, and you run back here, and at no point, do you look up and go, oh, wow, there's an arch up there, and oh, wow, and like those things go all the way to the top, and things like that. So there's going to be a need to like start putting the really visually impacting things more in your face. You're going to need lighting design that's going to be far more dramatic. You're going to need, there could be an entire thing where Hollywood set designers now have jobs in, and I know it's like boo hiss Hollywood, but these are people who understand, lighting and getting it all done right so that your view is drawn to an area, maximizing depth, things like that. And obviously, you're going to need a game design that leverages the technology effectively. If it's the same game, but it just keeps looking better and better, at some point that gets, you're going to hit a wall on that. And if you innovate the technology, you have to ask yourself, how can I make the gameplay that much better? There's a potential if stencil shadows were available all the time that is going to be something that's interesting. And it's happened a few times. In some death matches you're running, a rocket shoots by your head, you see your shadow, and you see someone else's shadow right behind you. You're like, someone's right behind me. Things like that can matter. It adds a different dynamic, say, to, water. All of a sudden, now you have transparency, so water is not something you can hide inside anymore because people can see you. Things of that nature. So what we are beginning to see is that we've gotten the low-hanging fruit. We've got 3D, we've got really cool lighting, we've got this kind of stuff. So now it's going to have to really start shifting over towards content makes a big difference. Unreal looked fantastic. And why was that? When their triangle counts were just so much lower than Quake 2's or even Quake 3's. And, it's just vibrant textures and things of that nature. So that is going to be, I think, a big problem for developers and technology people as we move forward, is having really cool technology and having a very collaborative effort with the content developers and trying to maximize the strengths and weaknesses, because you can't just provide a tool and magically expect the level designers and the artists to just immediately understand their uses. That's in the old days, that was a given, because it'd be like, yeah, texture map triangle, make a texture, make a triangle. There was like no really like key to all that. Now with shader technology and their ability to go manipulate a lot of things, we can't take that for granted, and we're going to have to spend a lot more time educating the content people on the power of the tool so that they can properly leverage that, because otherwise technology will continue to increase, but things will remain the same in terms of what they're looking at until effectively, we could end up with something like the John Carmack of artists or level designers, who suddenly comes with a whole new vision of how things need to be done and comes up with something super vibrant and super dramatic. So anyway, that's like my long-winded way of saying that technology itself does not solve the problems. It has to work hand in hand with content, and that might seem like common sense, but so many people expect id Software Games or Tim Sweeney at Epic or anyone like that to be able to come up with new technology and have stuff look radically different, when in fact you need the content that matches it, and sometimes that content's not there simply because of lack of education. So the programmers really can't be throwing code over a wall and things like that. It's going to become a far more collaborative effort in order to reach the next level I mean, truly, the next level of visual quality is going to be from having like a really cool production process where you have great technology, a great process, and everyone understands all the limitations of the different pieces. Because before, game development was a bit more of a hack. You know, it's just like, here's the technology, and you're always overcoming some major hurdle. All right, so now I'm just going off. Okay, so questions and answers. So, yeah. Oh, yeah, thanks. Turn the lights. Anyone? Oh, hold on, my eyes are still adjusting to the blinding spotlights here, so I'm like trying to find. Yeah. Right. Now that everything's based on shaders, the text files from the client side, God awful easily modified. So there's going to be considering mixed between CRC and shader files or anything like that. This is purely multiplayer now. Okay, the question is actually sort of a larger meta question, which is now that so much is being done on the client side, how do we prevent cheating? We actually saw this in Quake 1 where people would, you know, make other models like these really big stars that stuck through walls. Or they would make everybody glow bright white, things like that. That's a pretty big deal. I mean, our first thing is we want to make sure they're not hacking the code. So the client-side binary stuff is very important. We may actually have to do CRC checks and things like that because to make someone no longer invisible is just opening up a text file. I mean, we would like to address that, but I mean, unfortunately, one thing we've learned is that hackers and cheaters have way more time than we do. And no matter what we do, they will work around it, and they will bypass any mechanism we do unless we make it a full-time job to avoid that. I mean, same thing with copy protection. We will need copy protection since this is going to be so focused towards deathmatch on the internet. But, you know, we're not going to put out, we're not going to spend 3 weeks working on copy protection. We're going to spend, an hour. And we're going to get the low-hanging fruit on that one so that people can't just automatically, whereas it someone actually may have to, open soft ice. And then they'll figure it out instantly. But, you know, that's life. What are we going to do? Other questions? 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 Oh, come on. All these people. Okay, yeah. You. Wait, hold on a second. I'm sorry, I can't hear you. Wait, I'm sorry. We have a race condition here. You, the guy in front, can you hold on just 1 second so that you, the guy further back, can... Wait, I'm sorry. Okay. Oh, hold on just 1 second. Okay, yeah, you. Right? The question is, well, I mean, we still use a BSP tree. I mean, we use it mostly for other things. But right now we filter your position down through the BSP, and then we just grab the PVS from wherever you are. But since we don't cut polygons, we do get a lot more overdraw as a result. Right, we're drawing the entire surface instead of the surface that would have been trimmed off to some other convex hull. Okay, sorry. I'm sorry? Oh, really? Okay, so there's someone else here with a question? Yeah. A single player id title? Define single player. Okay, so basically it's, why did you let Half-Life kick your ass, I think is the question. All right, we're all friends here. And they're not recording this, and it's not going to be posted anywhere. Because, okay, what's the right way of saying this? That's not what we want to do. There are people like Valve that will go off and do a phenomenal single-player game. And when I say single-player, I'm talking the traditional sense of single-player, as in the game where you run around, you kill monsters, people aren't connected to your machine, and there's like a point to it. That's the definition of a single-player game for me, all right? As opposed to just running around blowing shit up to blow shit up. And the majority of it prefers just running around blowing shit up. And so therefore that's the game we're interested in. We feel that our licensees, in a way, can take our technology and do a more interesting single-player game with it than we can. I mean, Valve has demonstrated amazing competency at doing that, and that's just the type of stuff that if we don't have an interest in doing that, and the only interest we have is to sell more copies, then we're probably not going to be able to do as compelling a single-player game as Valve is going to do. And, so that's not where we want to focus. And more importantly, we don't want to compete with Half-Life because Half-Life sort of solves that problem really well. We're not sure we could do it any better. So we're heading in the other direction, which is the one place that we have demonstrated the ability to do the best game is deathmatch. And everybody plays our deathmatch stuff. People are still playing Quake 1 years after it came out, and you can look at any of Quake 1's contemporaries and say, does anybody play that game today? No. Does anybody play Quake 1 today? Yes. There are still like almost 1,000 Quake World or Quake 1 servers running all the time on the internet at any given time. So that is obviously what we know how to do exceedingly well. We know how to make fun deathmatch. We know how to make fun deathmatch levels. I've never actually played Half-Life Deathmatch, but I mean, the consensus I've gotten is it's cool, but it's not as fun as id stuff. And we're willing to take that. It's like Valve can go off and do their like hardcore single player and do a good deathmatch. We are not going to go off and even attempt to go off and do a story and cutscenes and all this other stuff, because we'd pretty much lose interest halfway through the project. We're just going to concentrate on letting you run around and blow shit up, And I mean, that's our core competency, is blowing stuff up. So I mean, that's basically it in a nutshell. Now, once again, it's like we're really defensive about this. Quake 3 will have a single player, but it's the analogy that's been expressed is sort of like Mortal Kombat. You play against the machine, you're eventually going to be able to kick the machine's ass. Then at some point, you're going to feel like you can take on somebody else, and it becomes a whole new game. We have to have a single player for Arena for one reason, and that is if you're on the internet playing, by definition, you don't completely suck. But if that's the only place you get to play, oh, guess what? You're never going to learn, because all you're going to do is spawn and die. And people really tend to forget a lot of times how difficult it is, how unintuitive this whole mouse keyboard thing is. I mean, when I first played, I think when most people first played Quake, you spent your time doing one of three things: looking straight up at the ceiling, looking straight down at the floor, and dying in lava. And, there is a learning curve there. So, I mean, we have to take this single-player thing very seriously. We're going to have bots that on the very first level are stupid. As a matter of fact, bots on the first level probably won't even shoot at you. They're going to be drones. They're just going to like walk around and just be like doo-doo-doo, and if you can kill them, that's a pretty significant sign, because I've met people, like I said, who have a very hard time just not killing themselves on a deathmatch server with them, and that's it. So, I mean, there is going to be the progression, and at some point you're going to be comfortable enough that you can play the game competently against the bots, and then you're going to be like, hey, let's see how good I am against the net. And, I mean, the analogy to this is a lot of people learn how to play deathmatch at LAN parties and stuff with their friends who sucked equally bad. I had a friend of mine at the University of Florida who was a big id fan when we were in college, and he was like the best Doom player like amongst 8 people. But like, he kicked everybody's ass. He was just like, I am the Doom master, I rule. So as the legend goes, there was a SIGGRAPH in Orlando, and SGI was demoing Doom down there running on IRIX, and they were having a tournament. And he was like, I am the best Doom man in the universe. I will take you on. And like some 10-year-old kid just wiped him. Like, so demoralized. Like, in front of like the other people, like he completely dominated. But this kid just like spanked him like he was a little, he was just like, wah, wah. And that's sort of the same thing. It's like you can become really good in a vacuum, but there's a certain level at which you're the best player. I mean, I ran the same thing. When I worked at 3D Effects, we used to play Descent all the time. And I was like the Descent master. Then I went and visited Parallax. And I was like, I think I can take them. So they're like, hey, you want to play a game? And I'm like, sweet. So like, here I am like playing games. They all log in, and all their names were like the old cheat codes for like Descent 1. I was like, wow, they probably really know this game. And so I play, and I was like, okay, boom, okay, that's cool. He got in a hit. I'm just like out of the zone. Boom, okay, no, that's cool. I'll just get to the Mega Bomb. Oh, dang, okay. And it's like they just destroyed me, and it was like so demoralizing because out of my 10 friends at 3DFX, I ruled the universe, but like you go to Parallax and you just get completely and utterly destroyed. So we want to avoid that syndrome where you can like get up to a really good level. I mean, if you can beat the top bot in Arena, I mean, you're inhuman because it's never going to miss. So that whole strategy is just making sure it never sees you. If you can do that, you're going to do pretty well on the net. And there's going to be free-for-all and things like that. So you're going to get pretty good. But that's a big thing we want to avoid is this whole, you know, I think I'm a really good guitarist because I've never played around other guitarists syndrome. I'm woodshedding in a vacuum kind of effect. So single player is going to be very important to us, but in a manner that has not been traditionally associated with single player. And we're very comfortable with that. I mean, you know, who ever played Quake for the story, you know? And it's just like complete bullshit. And it's just like, we need a story, and the story is you run around and you kill a bunch of monsters. And it's like Quake 2, I've actually had, and this like freaks me out because people send me email and they go, no, really, I mean, the Quake 2 story was so compelling because I wanted to know, like, what were the Strogg, what were their motivation, and it's just, I was fascinated to get to the end, and I was like, dude, I mean, come on, dude, are you insane? And I mean, yeah, I guess there's 1 in maybe 1,000 people who really strongly feel that, you know, it's like, wait, what's my motivation for shooting the rockets right now? It's like, because you're about to get your ass kicked. No, but in the end, what am I working towards? And you know what? They can go play Half-Life, and we're really cool with that. When we're just appealing to the people who want to run around and blow shit up, and which is a lot of people, but maybe not as many people. If, you know, it's not the same audience that Myst is, so we don't expect to sell 4 million copies of Arena. I mean, we don't actually expect to sell as many copies of Arena as Quake 2. We don't expect to actually sell as many copies of Arena as Quake 1, which was outsold by Quake 2. Because it is, I mean, this is bleeding edge stuff, but luckily we have the resources that we can, you know, sort of make the gamble. And we would rather do it and see how other people fare. I mean, we're really interested to see how Tribes is going to work out. Unreal Tournament, obviously. I've heard that there's a Turok Arena, but I don't know anything about that. I don't know if like there really is a Turok Arena, and if there is, well, they're going to try it too. So a lot of people are exploring this area, and you know, starting off with this Starsiege stuff, and I guess Fireteam also. So it'll be very interesting to see how well a hardware-accelerated title that is primarily aimed at deathmatch is going to do, because it's going to be appealing to a very limited audience. So I mean, in the future, we're probably going to see this heading more like sports games. Because I mean, hell, if we sold as many copies of Quake, you know, as EA sells of like Madden, we'd be pretty happy. Because those sports games, or FIFA, man, if we could get like FIFA sales, be like, yes. So anyway, that's my long-winded answer to that. Yeah. Will Quake 3 be more or less modifiable than Quake 1 and Quake 2? It will definitely be significantly more modifiable. Quake 2's big thing was that all the logic ran on the server. There was no opportunity really for mod authors to go off and do like their own client-side presentation. Since we now have a server-side DLL and a client-side DLL, you'll be able to do some pretty intense mods. You know, I mean, some actually extremely intense mods with it. But unfortunately, the flip side of that is because it's so modifiable, people are going to be modifying it in bad ways. You know, like the editing shader files so that everybody glows hot white and things like that. But cheaters are, you know, just sort of a fact of life that you have to deal with. And when you're someone like us, where we share our technical information and you know, have just text files sitting in directories, our pack file structure is now just a zip file. So if anybody just like, you know, hey, I want to see what TGA they use, they just pop open WinZip. I mean, we do stuff like that because we don't attempt to obfuscate. The downside, I mean, the upside obviously is we have this awesome user community. We just have like, I think tens of thousands of people who are hardcore Quake and Quake 2 players. And that's a great feeling. The flip side of it is we have tens of thousands of hardcore Quake and Quake 2 players who are pissed off because of cheaters. So, you know, it's sort of a double-edged sword. Other questions? Yeah. Well, I guess we'll find out what it looks like on a TNT. So the question is, what does the vertex lighting look like? And you know what? This is like completely untested, and this could crash. So like, don't expect too much. Yeah. Vid restarts are always creepy. So it looks like that. The world got darker. Okay, the world got a little too dark. Oh, okay. Oh, wait, hold on. All right, wait. Yeah, put that in the manual. Everything's too dark. Turn off your lights. Oh, wait, did that come back? Wait. Okay, wait, hold on, wait, let me crank gamma. Yeah, okay, cool. So, I mean, it doesn't look horrible. I mean, it just sort of looks washed out. This is, I mean, obviously there is a bug here. You get these cool little vertex artifacts right there. So if I do that, hey, guess where that vertex is? But, and you know, this place gets well lit. But it looks good enough. Wow, those are like old school Descent shadows. It's really cool. Descent use vertex lighting. So just not bang on. Turn, damn it. Okay. So, hey, that's vertex lighting. It looks pretty good, and it runs a lot faster. So, I'm glad you mentioned that, so I'll have to go remind John to fix that. Wow, that's really dark up there, isn't it? Feel the pain. Okay, so it doesn't look bad. It's not like horrible artifacts. I mean, part of that is a byproduct of, okay, it doesn't work on things like that. And you don't get dynamic lights. So, I mean, it doesn't look horrible. It's not like some completely gross rendering mode. It's like, ew, oh, yuck. It works well enough, and it will work, you know, fairly well on the Pro Media too, once we get it fixed. And it will run twice as fast, and I don't think it will give anybody a competitive advantage. You should have the same amount of overall brightness. You'll just have linear interpolation artifacts. Thanks. Okay, yeah. Okay, what is my opinion of the consoles? I slept through the PlayStation thing, so I don't have an opinion on that other than I've seen their specs and their specs, so whatever. I think Dreamcast and PSX2 should be able to run stuff like this fairly effectively, but I don't have enough knowledge about our console development. We do all of our console stuff externally. We have some contractors, other companies do it. The last console game that it did internally was like Jaguar Doom. So I'm not up to speed on that stuff, but I believe on my brief conversations with John about it that, I mean, he feels like it should be fairly effective, the very modern type stuff. I know we've had, it's been somewhat of an issue with like the cart-based stuff like N64, Quake 2, which I think should be shipping any day now from what I understand, but I mean, that takes a lot of effort trying to compress that down. PlayStation has its own set of issues. I mean, there was actually a Saturn version of Quake, believe it or not, and I was like, wow, that's really cool, but it takes a lot of work. I mean, they basically can't take the code and just recompile. Or even massage stuff. You almost pretty much have to start from scratch. Other questions? Yeah. You mean like the tools? Okay. What is our strategy? This is the question. What is our strategy for keeping the pre-processing out of the way of the artists and the designers from having to do stuff? Like our BSP times, I assume you mean things like that? Okay, do you mean in computation time or do you mean in, okay. So how do we make that make that fast? First thing you do is you blow $500,000 on a Silicon Graphics supercomputer. That helps. Unfortunately, and this is sick as a complete aside, is that our SGI supercomputer, 16 processor, MIPS R10 cans, blah, 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 is about the same speed as a quad processor Katmai today. So first we solve it by brute force. It's the money versus time trade-off. The second thing is there's like this weird threshold of pain that the level designers go through where they decide that 15 to 20 minutes is as much as they will tolerate. And if we if John went off and optimized all the tools so that they ran in 15 seconds on maps that currently take 1 hour, within 3 days, it would still be running at 15 minutes. Because they do just enough detail and work to make it run at 15 minutes. Because if it takes less time, they're like, oh, I can get more detailed. And they'll just, add some more lights, add some more geometry, and they'll just keep doing, because 15 minutes is their magic threshold, because that's enough time for them to go, to the bathroom, grab a drink, talk to someone, come back, it's done. If it's 5 seconds, then they have to sit there and keep working. But if it's longer than that, then there's no instant feedback, because then they'll go do it. It'll take 2 hours, and they'll come back and wait, what the hell did I change? So so that's it. A lot of it's just a psychological thing. There's no real technology to it. One thing that we have done, and we did this in Quake 2, is we had the concept of detail brushes, where you could flag some things in the world and just say, do not carve the BSP. And because you would have a simple box room, then you would put a square cube on it, and it would just chop the world into pieces. And you'd be like, you know what, this isn't very important for Viz, specifically for our visibility pre-computations. So let's not even just factor it in for Viz, things like that. Other questions? Yes? Okay, could we just do game engines in the future and not make games? We could, but we are actually religiously opposed to that, because we do not feel a game engine is valid until you have written one game on it. Until you do that, then it's just theoretically going to work. Then someone's going to license your game engine that's never had a game written for it and figure out, okay, do I have to stop? No, I have to? Okay. I have to go. I'll be up here. Wait, can I go down there and talk? Okay, thanks. All right. It's Dad. All right, thank you.